Today we're going to look at a few inverse trig functions and see what kinds of questions we can answer using those inverse functions. But first, I want to give you a brief introduction to inverse functions in general to serve as a foundation for this concept. Remember from algebra that a function is often written as an equation with an input, usually x, paired to an output, usually shown as y. The rules of functions are simple. Every input can have one and only one output. The example that I've commonly used in class is that of a restaurant menu. Every item on the menu must have one price. Function notation, f of x, is often used interchangeably with y. A function's inverse is the rule or equation which swaps that function's domain and range. In other words, all of the inputs become outputs. The pairings remain, however. So if you have the ordered pair 1, 6, the inverse function will take an input of 6 and return an output of 1, giving the ordered pair 6, 1. The function notation for an inverse function uses this -1 exponent. Be careful here. This notation is not asking you to apply a negative exponent, multiply by -1, or do any arithmetic at all for that matter. It's just notation, giving you a visual indication that you're looking at the inverse of function f. Let's look at a specific example. Suppose I have a nice simple linear function, f of x equals 2x plus 4. I could write this instead as y equals 2x plus 4. It means the same thing. To find the function's inverse, we're going to exchange the input and the output variables. So x becomes y and y becomes x. Now I have the equation x equals 2y plus 4. To write the inverse function in slope-intercept form, we're going to solve for y here, which I've shown on the right-hand side. We'll subtract 4 from both sides of the equation, then divide both sides of the equation by 2. Be careful simplifying here. Both x and the 4 get the division because there's 2 terms on this side of the equation separated by subtraction. Simplified, I have y equals 1/2 x minus 2. Now, it seems like a good idea to prove to ourselves that these two functions are indeed inverses. As I mentioned earlier, if we did this right, any ordered pair from the original function should have the x and y values still paired but swapped. Let's try that ordered pair 1, 6 again. In the original equation, I'll replace x with 1 and solve for y. I get 2 times 1 plus 4, which is 6. Perfect. For the inverse function, I'll replace x with 6 this time. That'll be 1/2 of 6, subtract 2, that's 3 minus 2, which is 1. Awesome, it works. This inverse function takes all of the solutions, that is the ordered pairs, from the original function and inverts them. Here's another visual representation of what inverse functions are doing. We can see from the table of values that each set of x and y values are still paired, but the domain becomes the range and the range becomes the domain. On the graph, it looks like this. In part 2, we'll go on to look at inverse trig functions and how they can be used to answer questions with right triangles.